Hello everyone, welcome to the channel Learn Math with Shobita. Today in this episode I am discussing some questions from linear algebra. First question, let M be a square matrix with real positive entries such that each column adds up to 1. Then which of the following statements is not true? Option A, an eigenvalue of M is 1. Option B, the sum of the entries of an eigenvector corresponding to an eigenvalue lambda not equal to 1 is 0. Option C, there is no eigenvalue lambda not equal to 1 such that modulus of lambda greater than or equal to 1. Option D, the sum of the entries of an eigenvector corresponding to eigenvalue 1 is 0. So I will take an example. Using a counter example, let us analyze each option. So solution, given M be the square matrix with the real positive entries such that each column adds up to 1. So let M, I will take a 2 by 2 matrix with each entry adds up to 1. So I will take, this is 1 by 2 column, and here it is I will take it is 3 by 4 and 1 by 4. Clearly the sum of entries in the first column is 1 as well as sum of entries in the second column is 1. First option, an eigenvalue of M is 1. This is true because we have one of the result. If sum of entries of each column, sum of entries of each column or each row adds to a single value, then that value is an eigenvalue. Then that value is an eigenvalue. Okay. Therefore, 1 is an eigenvalue of M. Eigenvalue of M is 1. Okay. 1 is an eigenvalue. Okay, this is true. Next, sum of entries of an eigenvector corresponding to an eigenvalue lambda not equal to 1 is 0. So let us find another eigenvalue of this. We have here trace of M is equal to 1 by 2 plus 1 by 4. So this will be 3 by 4. Okay. 2 plus 1, 3 by 4. Trace is 3 by 4. We have sum of eigenvalues is trace. So lambda 1 plus lambda 2 is equal to 3 by 4. Lambda 1 is 1, we know. Therefore, lambda 2 is equal to 3 by 4 minus 1. This is minus 1 by 4. Another eigenvalue. Okay. Now let us find the eigenvector corresponding to lambda 2 equal to minus 1 by 4. So let us analyze A minus lambda is minus 1. So A minus minus means A plus 1 by 4i into x is equal to 0. Sorry, here M. Okay. So analyzing that. Now let us find an eigenvector corresponding to lambda is equal to minus 1 by 4. So I will calculate this M plus 1 by 4i into x equal to 0. So after the calculation, I got 1 comma minus 1 as an eigenvector corresponding to lambda is equal to minus 1 by 4. If I add entries of this eigenvector, I got 0. Therefore, the sum of the entries of an eigenvector corresponding to an eigenvalue lambda not equal to 1 is 0. This statement is true. Further, there is no eigenvalue lambda not equal to 1 such that modulus of lambda greater than or equal to 1. This is also true because here M is a 2 by 2 matrix. It has only two eigenvalues. One is 1, another one is minus 1 by 4, and its modulus value is less than or equal to 1, and no other eigenvalue with the modulus of lambda greater than or equal to 1. So this statement is also true. Therefore, the statement which is not true is option D. That is, sum of the entries of an eigenvector corresponding to eigenvalue 1 is 0. This statement is not true. Next question. Let W1 and W2 be subspaces of a vector space V such that W1 intersection W2 equal to 0. Singleton set 0. Let W1 belongs to W1 and W2 belongs to W2 be non-zero vectors. Which of the following is true? Option A. The set containing W1, W2 and set containing W1 plus W2, W1 minus W2 are both linearly independent sets. Option B. Set containing W1, W2 is linearly independent, but set containing W1 plus W2, W1 minus W2 is linearly dependent set. And option C and option D are like that. I will not read each one. So let us solve the question. Okay. We are given that W1 and W2 are subspaces of V. Okay. Such that W1 intersection W2 equal to 0. Further, W1 belongs to W1 and W2 belongs to W2 are the two non-zero vectors. Now let us check whether the set containing W1 and W2 is linearly independent or not. For that, consider the linear combination C1 W1 plus C2 W2 equal to 0, where C1 and C2 are scalars. Now C1 W1 equal to minus C2 W2. So this implies that C1 W1 belongs to W2 and C2 W2 belongs to W1. Already this C1 W1 belongs to W1 and C2 W2 belongs to W2 because W1 and W2 are subspaces. Okay. So therefore C1 W1 and C2 W2 both belongs to the intersection W1 intersection W2. But we have W1 intersection W2 is the singleton set 0. Therefore, we must have C1 W1 equal to 0, C2 W2 equal to 0. This gives us C1 equal to 0, C2 equal to 0 because both W1 and W2 are non-zero. Therefore, trivial relation is the only linear combination between the vectors W1 and W2. Therefore, the set containing W1 and W2 is linearly independent. Next, consider the linear relation between W1 plus W2 and W1 minus W2, where A and B are scalars. So this implies A plus B into W1 plus A minus B into W2 equal to 0. So solving this, since W1 and W2 are linearly independent, we must have A plus B equal to 0, A minus B equal to 0. So this gives A equal to 0 and B equal to 0. Therefore, W1 plus W2 and W1 minus W2 is linearly independent. Hence, here the option A is true. That is, the set W1, W2 and W1 plus W2 or W1 minus W2 both are linearly independent. Next question. Consider the linear transformation T from R3 to R2 given by the matrix 1 0 1 0 1 1. Which of the following is a true statement? You see the options. I will solve the question. So given matrix of T is 1 0 1 0 1 1. So rank of this matrix is 2 because these two rows are linearly independent. So rank of T equal to 2. Now nullity of T is dimension of domain minus rank of T. This is by rank nullity theorem. Okay. According to rank nullity theorem, rank of T plus nullity of T is dimension of domain. Here domain is R3, its dimension is 3. Therefore nullity of T is 1. nullity of t equal to 1 implies kernel of t is not equal to 0. Okay, so this implies t is not 1 1. We have the theorem that is since t is 1 1, if and only if kernel of t equal to 0. So here nullity of t equal to 1 implies kernel of t not equal to 0. This implies t is not 1 1. Further, rank of t is equal to 2, which is equal to dimension of the codomain. Here codomain is R2, its dimension is 2. Therefore, range of t is equal to codomain, which implies t is on 2. Therefore, t is on 2 but not 1 1. So, therefore, option B is true. Next question. The dimension of the space of n by n matrices, all of whose components are 0 except possibly the diagonal components is. Given that the matrix has non-diagonal elements as 0 and diagonal elements are non-zero, a n by n matrix has n diagonal entries. Therefore, here dimension is n. Option D is true. Next question. The matrix R of theta associated with the rotation by theta equal to pi by 4 is. Option A, B, C, D are given like this. Now, let us solve the question. The matrix R of theta is given by cos theta minus sin theta, cos theta. Here theta equal to pi by 4. Substituting the value, cos pi by 4 1 by root 2, sin pi by 4 1 by root 2. We get like this. Now adding and multiplying root 2 to the numerator and denominator, I got this is root 2 by 2 minus root 2 by 2, root 2 by 2, root 2 by 2. Therefore, option D is true. Thank you friends. Please share and subscribe the channel.